So that's the vanilla reinforced agent, and it has. We're gonna go through the train function, and we're gonna go through what's happening, but there are some parts for you to fill out, and then when we get there, we're gonna take like 20 minutes to fill it out, and then we're gonna go through it together. Yes. I'll make it bigger. Just a second. Is this good?
Yeah. And then
Okay, so we're gonna initialize the go through the train function, and we're gonna go through what's happening.
The good news is the audio is fixed.
sorry, go.
Okay. So we're gonna initialize our weight matrix, right? And we're gonna give it like some input size from the environment. So the input is gonna be the size of the dimension, and the output size is gonna generate like number of actions I can do. So it's gonna be a weight matrix that has like number of input dimension times number of actions as output. And what are the actions I can take? They go from 0, 1, 2, 3, 4, 5. Like this output size dimension array, so I'm gonna say range output size. And for training, I say, okay, I have some environment, and I say these are the number of episodes I want to play. These are the number of maximum steps I have in an episode. This is like kind of my gamma. It's like the future discount. And this is my learning rate. And I say, okay, this is the total reward of that episode. This just stores for each episode I played the total reward. And for range number of episodes I go through, and I reset the environment. This gives me the start of the game, essentially. This is the reward of the current episode. These are like the rewards of each step. And this is like each gradient. For each step, you're gonna save the gradient, because if you look here, you kind of have the gradient for each step. And we're gonna say self.policy returns me kind of, this is just a forward pass. So self.policy is just forward pass. So you do the matrix multiplication, and then you apply your softmax. And then we select, because softmax is gonna be like a probability vector. It's gonna sum up to 1, and then we're gonna, okay? And then we're gonna select like a random action from that policy. Like we select randomly from that policy an action. Say if this policy says you have 99% to do action 1, with 99% probability you're gonna select action 1. We do the action, we get our next state, we get our reward, we get our done. And then we say, here we're gonna play a card pool. So we say if we're done, we give an additional minus 10 points. And if we have rewards, we just append the reward. So this is just the reward of the current state.
So this is fixed.
Yeah, this is what we get from the game. And if you have your own game, let's say you want to do image classification, or you want to chat or whatever, you have your own reward function. You have to write, you have to come up with a reward function. So there's a paper about chatbots and reinforcement learning. They have a really nice reward function. So it's a paper about doing recommender system with reinforcement learning. They also have a very nice, just look at those reward functions. And we have some, I don't see this back anymore. And say we give a state, we give the probability vector, we get the action, and we're gonna take this to construct our gradient for that step. And then we store that gradient in a list, and then we say, okay, episode reward is the total reward, and then we say our state is the next state, and then we play again. And at the end of the episode, we say, okay, we go through all our gradients, we multiply it with the learning rate, then we get our future discounted rewards, which is just basically I sum up gamma times the reward. It's just a weighted sum of all the futures. And then we say update my weight saying gradient times future discounted rewards.
So when we have 2 stars here,
Hmm?
gamma and then 2 stars, R.
This is gamma to the power of r.
Okay.
Like this is for t and r, you sum it up. So you calculate like this is my reward plus gamma of my reward plus 1, like from the next t plus 1, t plus gamma squared, reward t plus 2, and so on and so on and so on. And we sum over it.
Okay. Thank you.
Essentially, this is what this does here. Starting from E. So if we go next step, we go through. And that's how the gradient. So that's the policy. It just does a dot product between state and the weight matrix. And then we do a softmax activation function. And then we just, what's this? This is 0. Definitely not a 0. So here it was a 0, it replaces it with a O. You see it? And then you return the policy. You successfully generate the policy with a forward pass. So this is how we kind of calculate the Jacobian matrix, which basically is the gradient for each action, right? Instead of calculating the gradient for one action, we calculate on with one step the gradient, like the not the gradient, sorry, the derivative of the activation functions for each action at the same time. So because of each action at the same time, we just calculate the softmax gradient, which is like the softmax derivative, and then we select the action we need. So this is what this action selects us for what we need. And then we need to do the backprop, which is kind of like a dot product of dlog and the input. And then now we have a gradient, we need to divide it with the probability of the action. So this is this part here. And then you have your gradient. And that's it. And then, because we create our environment, we have some random seed we set, and then with the environment, and this is like the shape, this returns you like 4 comma tuple, so 0 gives us the dimension, and this gives number of actions, and then we train the environment for 5,000 steps for 500 step size. And just a second. Anyone has questions for that? Any has questions for the code? Like you can organize yourself in groups or in groups of 3 or wherever, or talk to your neighbor. Because now for the next 20 minutes, you're gonna try to, like there are a few things. All these where it's equal and then it has this kind of comment. You should fill it out. So it's basically 3 lines you have to fill out. You managed to get the solution? Great. So who got a solution at the end? 2 teams? Here as well? Huge improvement. Anyone wants to come and code the solution himself? Oh, I'll do it quickly. Okay, anyone at home got the solution? I don't see the joke. Oh, I see the chat, but it's like, can you make it bigger? Oh, you don't see. It's okay, just leave it. Anyone at the home who got the solution? Feel free to share in the chat. State dot. So self.w, and this is basically mp.exp of h. And this is like state.reshape. Come on, -1. That's how I do. Sorry, -1. Come on. Dot. This is how I did it. You don't necessarily have it to do it this way if you are paying enough attention to know which order to multiply those vectors. You just need to make sure that they have the right dimension, else it's gonna complain.
You missed the E after reshape.
Thank you. And that's gonna train Oh, thank you. And that's gonna train, and it's gonna take a very long time to train. Not very long time, but it takes a lot of episodes. But we're fast at the episodes. And so far it does do pretty randomly, like, and then suddenly it gets it right, and then it does very consistently. It does really well. So if you see it start popping up, like 489 is the maximum score we can get. We share the screen.
Yeah, stop screen share and then restart.
So we are resharing the screen while we are training. It's a good time to share the screen. Share screen. No. Oops. Is it better? You see, now the policy is kind of getting there. It's doing really good. So, like I said, this is card pull. So once you have more than 100 points consistently, you kind of consider it as a success. And now we get like the maximum score over and over again. So we get 489. I looked into it. Why we get 489 as maximum possible score is because in training we say we go 500 steps, right? And if it's also in the thing is like the last step, the 499, it says I'm done and doesn't give me a point. And then I say, oh, if you're done, I subtract 10, so we are 489. Because if it would give you a point for the last step, I would make 490 and not 489. So it's almost done. Any questions?
Could you go back to the last part of the solution? I know it's
The gradient?
yeah. What did you do the reshaping there?
Just to like the state is, I think 4 times 1, and the other one is 1 times 2, and either you make the dot product in the way you need it, or you just reshape it and do the dot product. Like you need to make sure that you get like our matrix is 4 times 2, so you need to get a 4 times 2 matrix at the end if you do the dot product. Like you get a gradient. The gradient is for every weight, and our weight matrix is 4 times 2. And I'm just I had issue finding the good. I don't know why I did it this way, because it works. And you see, now we get like maximum score, close to maximum score for each run. And let's hope we have no. Okay, I have the video already saved, so I'm gonna show you the video before I'm rerunning the agent, so at least we have something to look at it. So it does really well, but it also fails at one point. I feel like here at the very end, it's gonna like it looked like it's gonna move all the way to the right because the pole was all the way over. But it's balanced the pole, what it's supposed to do. Let's see. So I have this kind of utils. This has like a monitor, and the monitor writes it to file. And then that utils file, Python file, is also like a code which kind of makes a web embedding for a video, because it's like everything is Google Colab. And all of these things has conflicts with different OpenAI Gym packages and other things. So if you don't upgrade your AI Gym package before importing it, it doesn't work. And then if you upgrade after importing it the first time, it just throws an error. So it's a bit fickle. So this kind of concludes the first major algorithm part for this lecture. We have a second, is the deep deterministic policy gradients. Are there any questions? So who would feel confident in I understand what's happening here, what's understand in this reinforcement algorithm? just like roughly 50% of people. That's okay.